The photoelectric effect provides evidence for the particle nature of EM radiation. Which of the following observations of the photoelectric effect could also be explained using the wave nature of EM radiation? So part A of the question says that the emission of photoelectrons is instantaneous. So to explain this in detail, in such a way that makes complete sense, we have to go over the wave and particle model of EM radiation. So just before the photoelectric effect experiment and Einstein's predictions, physicists believed that light traveled as a wave. What does it mean for light to travel as a wave? And how should it affect the photoelectric effect experiment? Well, if light travels as a wave, it transfers energy continuously. What are the implications of this? Let's draw a quick diagram. So here is our light source, here is our wave, which is transferring energy continuously to the electrons in this metal surface. So in the wave model of EM radiation, physicists believe that there should be a time delay from when you first switch on your light source to when you first see electrons being released from the metal surface. They also believed that that time delay should depend on the intensity of the light source. Why is this? Well, if electrons require a certain amount of energy to be liberated from the metal surface, the work function is that minimum energy, and if they're absorbing that energy continuously from the light source, then a certain amount of time must pass until the electrons have reached that threshold of energy that they need to leave the metal surface. If you change the intensity of your light source, then the time it takes for the electrons to build sufficient energy to leave the metal surface will also change. Intensity is power over area. So the more intense your light source is, the more power, the more energy per second, and the more energy per second means the electrons will gain the requisite energy to leave the metal surface in a shorter amount of time. That means the time delay will be lower. The opposite should also be true in the wave model. A low intensity light, a dim light, means the electrons absorb energy at a lower rate, and it'll take them longer for them to build up the energy they need to leave the metal surface, and the time delay will therefore be bigger. What about in the particle model? Let's just draw a quick diagram of that. Again, here is your light source. So in the particle model, light travels as photons with energy hf. They are discrete packets of energy, and that energy depends on frequency. The electrons in the metal surface can only absorb one of these photons at a time. There's a one-to-one interaction. This means they must absorb all the energy that they need to leave the metal surface in one go from one photon. They can't absorb multiple photons and gradually build up the energy they need to leave. It must be all from one single photon. This means the energy of that single photon needs to be above the work function to liberate the electron. So what does that mean for the time delay? Well, there won't be one. The photon is emitted from the light source almost instantaneously. It travels across this gap at the speed of light, so that's a very short amount of time, and it's then absorbed by the electrons in the metal surface almost instantaneously as well. That whole process, from emission to absorption, is almost instantaneous. It takes next to no time. So long as the individual photons have enough energy, i.e. their frequency is high enough, they'll liberate electrons from the metal surface as soon as you turn on your light source. There is next to no time delay. It's an almost instantaneous process. It doesn't matter if you increase the intensity. This has an effect in the wave model. Increasing the intensity, if you remember in the wave model, makes the electrons leave in a shorter amount of time, and vice versa. In the particle model, if you increase the intensity, this will simply increase the number of photons that you have crossing the gap from your light source to your metal surface per second. This will increase the number of electrons that you then have leaving the metal surface per second, so it increases current, but it won't affect the time it takes for one photon to be ejected, for it to then travel across the gap and then be absorbed. That process will still be almost instantaneous. It will still take negligible time. So whether it's an intense or a dim light source, in the particle model, as long as the frequency of these photons is above the threshold frequency, electrons are emitted instantaneously. Okay, so that's the fundamental theory discussed. We can now go on to the options and get through them fairly quickly now that we've established the groundwork. So option A, the emission of photoelectrons is instantaneous. This is a particle model phenomenon, as we discussed, not a wave model phenomenon. In the wave model, there should be a time delay. In the particle model, they gain their energy instantaneously. So it can't be A. We're trying to see which of these options can be explained by the wave nature of EM radiation. On to option B. The maximum Ke of photoelectrons depends on frequency. Let's have a look at Einstein's photoelectric effect equation. So that is HF is equal to phi plus Ke max. From this equation, we can see that the frequency of the photons determines the maximum kinetic energy of the electrons. That's if we assume that the work function remains unchanged. That work function depends on the type of metal used. So, frequency determining maximum kinetic energy is a particle model phenomenon. HF is part of the particle model. Each particle has this energy, and they determine the maximum kinetic energy of the electrons. In the wave model, it's intensity that affects the kinetic energy of the electrons that are released. If you have a higher intensity, you have more energy being transferred to the electrons per second, and they end up leaving the metal surface with more kinetic energy. Frequency doesn't affect the intensity of the wave, and therefore it doesn't affect the kinetic energy of the electrons. Rather, it's the amplitude of the wave that intensity depends on, not frequency. So this can't be explained by the wave model, but it can by the particle model. So the answer isn't B. Option C, the rate of emission of photoelectrons depends on intensity. This can actually be explained by both models. In the particle model, more intensity means more energy per second, which means more photons per second. More photons per second means more electrons are being released from the metal surface per second. And in the wave model, if you increase the intensity, again you have more energy being transferred by the wave per second, which the electrons are absorbing continuously, and a higher power means more electrons will gain the required energy to leave the metal surface each second. Higher intensity means higher number of electrons leaving the metal surface per second. That means a higher rate of emission. So C is true in both models, so our answer is C. And we'll go over D as well to see why it can't be true. There is a minimum frequency for emission of photoelectrons to occur. This goes back to the idea of a threshold frequency, which is true in the particle model, but not in the wave model. It's true in the particle model because electrons are absorbing photons of energy HF in a one-to-one interaction. Therefore, the energy of a single photon must be above the work function, and therefore the frequency of those photons must be above a certain value too, because the energy of the photon is HF, and that's called the threshold frequency. In the wave model, frequency doesn't affect the power that the wave transmits per second, it's amplitude that affects intensity and therefore power. In the wave model, intensity affects the time of emission, as we discussed before. So a high intensity wave will decrease the time it takes for electrons to leave, and a low intensity wave will increase the time it takes to leave. But for either high or low intensity, this electron will eventually build up enough energy to leave, and frequency does not affect that process. That's why it can't be D.